It's Paul Bamberg with the introductory video for the 4th class in Math 217. You should watch this before class on September 10th. The subject is partitions and filtrations. So let's think about how we might try to generate a sigma field in general. We start with a collection of events, a collection of subsets of the sample space to which we'd like to assign probabilities. We could lock out and discover that this collection is a sigma field, but in general we won't be that lucky. We might find out, for example, that we've included a set but have neglected to include its complement, or that we've included two sets but neglected to include their union. This collection of subsets is certainly going to be a subset of the biggest possible sigma field, the power set 2 to the omega, but it's also going to be a subset of a variety of sigma fields that are smaller than 2 to the omega. And if we want to assign probabilities to the events in A and do it in an efficient manner, we want to work with the smallest sigma field that will do the job. We call this the sigma field generated by A, and we'll denote it by fancy f of A. What do we mean by smallest? Well, there are two equivalent ways of describing this. You can say any sigma field that contains A also contains f of A. So any other sigma field is at least as big as f of A, and f of A is therefore the smallest. Or equivalently, we say we just look at all the sigma fields that contain A, form their intersection. That intersection is the smallest sigma field. There's a very nice example in Dineen's textbook, example 310, where the sample space is finite, and we can just use the axioms for a sigma field to determine this smallest sigma field. We have to include the entire sample space. Then we have to take complements of the sets that are in A because they're required to be in the field. And we form unions until eventually, by taking complements and unions, we don't include any more subsets, and we've got the sigma field that we want. Let's look at a more systematic way of doing this. Here's a simple special case. Omega is a finite sample space. In this case, I believe it is the numbers 1 through 10. And the subsets that we want to be able to assign probabilities to include the subset 2, 3, 4 and the subset 4, 5, 6, 7. Those two subspaces, those two subsets, do not form a sigma field. Their complements are missing. Their union is missing. What are we going to do about it? Well, the first thing we do is to form the intersection of those two sets, the elements they have in common. That consists simply of 4. So B0 is the set that has nothing but 4 in it. And then we remove 4 from both those sets. We form set differences, which we'll call B1 and B2. That'll give us 2, 3, and 5, 6, 7. Now we have 3 disjoint sets, but we haven't included everything. We still have to ask which elements of the sample space are still not included in any of our sets, and those will form B3. That's the complement of the union of the 3 sets we've already got, B0, B1, and B2. And in this case, it will include 1, 8, 9, and 10. What have we done? We've broken the sample space, 1 through 10, up as the disjoint union of 4 sets. And if we look at all possible unions of those sets, it must be a sigma field, and by the way we constructed it, it includes A1 and A2. In fact, it's precisely the smallest sigma field that does that, the f of A that we're looking for. Now let me define the term partition. Let's think about any possible case. The sample space might be finite, might be countably infinite, might be uncountably infinite. In any of those cases, what we mean by a partition is a collection of subsets that meet two requirements. First, the subsets have to be pairwise disjoint. Consider any two of them. Their intersection is the empty set. And notice I've carefully subscripted with alpha and beta to avoid any implication that I'm only talking about countably infinite sets. Second requirement for a partition is that the union of all the sets in the partition, this could well be an uncountable union, is the entire sample space. Now, when we perform an experiment, precisely one of the events in the partition will occur, because something will happen, and that something cannot belong to two different events in the partition. They're disjoint. It must belong to at least one of the events in the partition because their union is the entire sample space. If we go back to example 310, the four sets in the partition were 4. We got that as the intersection. 2, 3, and 5, 6, 7, which we got by removing the intersection from the initial two sets, and 1, 8, 9, 10, the leftover thing. And in the case where the sample space is countable, we can easily prove the general result that's suggested by this example 3.10. If you have a countable partition of your sample space, then the smallest sigma field that includes everything in that partition is just the collection of all possible unions of sets. Think about this and it becomes fairly obvious. If you had a sample space consisting of 1, 2, 3, and 4, then you could take all possible unions and get 1, 3, or 2, 3, 4, or so on. Here we're doing the same thing, but we're doing it with the four sets that are in the partition. Here's a clever alternative way of looking at this same idea. We now know how, given a partition, we can easily create a sigma field. But we can do this the other way around. Given any sigma field, we can create a partition. That's what example 3.10 was all about. And in order to formalize this idea, I want to define the term equivalence relation for you. An equivalence relation is a relation that has the same properties as equality. I'll denote an equivalence relation generically by a tilde, and it has to satisfy the following axioms. It's reflexive, that is, x is in the same equivalence class as x. That's like saying any number is equal to itself. It's symmetric. X is related to y if and only if y is related to x. That's like saying if x is equal to y, then y is also equal to x. And finally, it's transitive. If x is related to y and y is related to z, then x is related to z also. That's like saying for equality, if x equals y and y equals z, we can conclude that x equals z. Now, given any x in our sample space, we can construct an equivalence class. This is x in square brackets. This is the equivalence class containing x, the set of all y's in the sample space for which the equivalence relation x is equivalent to y is true. Here's a simple example. An equivalence relation that works for the integers symbolized by m tilde n is take the difference between the two numbers, that integer is divisible by 3. And in this case, there are precisely 3 equivalence classes. You may have seen them in another course as the elements of the finite field called Z3. So the equivalence class of 0 includes all the integers, positive, negative, or 0, that are divisible by 3. The equivalence class of 1 is the collection of integers that leave a remainder of 1 when divided by 3. The equivalence class of 2 of integers that leave a remainder of 2. And each of these classes, in fact, has an infinite number of different names. The equivalence class of 0 is also the equivalence class of 3, is also the equivalence class of 12. You can name it after any integer that's divisible by 3. This simple example illustrates a very general property of equivalence classes, though. Either they're equal. The equivalence class of 1 is the same as the equivalence class of 7. It consists of all integers that leave a remainder of 1 when divided by 3. Or, if equivalence classes are not equal, they're disjoint. The equivalence class of 2 and the equivalence class of 3 have no elements in common because there's no integer that leaves a remainder of 2 and also a remainder of 3 when you divide it by 3. Every element has to belong to some equivalence class because the element x has to belong in the equivalence class generated by x. And since these equivalence classes are disjoint, and everything in the sample space belongs to one, these equivalence classes form a partition. That's why we're talking about equivalence classes. Now let me give you the key result. This is proposition 3.16 in Deneen, and I call this the love and marriage equivalence relation. See if I can sing the song. Love and marriage, love and marriage, go together like a horse and carriage. This I tell you, brother, you can't have one without the other. So it's you can't have one without the other that defines this equivalence relation. X and Y are in the same equivalence class if whenever you find a set in the collection of subsets A, it also includes Y. Or more formally, for any set B, X is in the set B if and only if Y is also in the set B. Either X and Y show up together or they're both missing. Now, if we've got this collection of sets, there are going to be some elements in the sample space in general that aren't members of any such set. That forms an equivalence class. If you consider any pair of them, they're both absent from any set you might consider. Otherwise, if we want to form the equivalence class for some element x, we simply look at all the sets in the collection A that have x as a member and find out which elements they have in common. The elements that always show up when x shows up, and that's the equivalence class consisting of the y's that always go together with x. These equivalence classes always form a partition, and if this partition is countable, which will frequently be the case, then we get our smallest sigma field that includes A by just saying we want to consider all possible unions of equivalence classes. You get plenty of practice in doing this when you work on the problems that we'll be solving in class. Now let me introduce the concept of filtration, which is going to be very important when we start applying these concepts to securities markets. If we have a partition, we can make a finer partition simply by subdividing some of the sets in our original partition. For example, we could have started by partitioning possible rolls on a single die into small numbers 1, 2, 3 and large numbers 4, 5, 6. Then we could create a finer partition by subdividing each of those into its even numbers and its odd numbers. If you have a sigma field based on a finer partition, it's going to have to contain more sets. Now we carry out an experiment and we ask, did event A occur? We're allowed to ask that question only if A is in the sigma field. If we have a larger sigma field, which is based on a finer partition, that means we can ask more detailed questions about the outcome. Here's a lovely example, the game of craps. The way you start a game of craps is the shooter takes a pair of dice and rolls them. And there are basically three sorts of things that can happen. If the shooter rolls a total of 7 or 11, he or she wins the game immediately. Rolling 2 or 3 or 12 means you lose immediately. That's known as crapping out, which gives rise to the name of the game. And finally, with any other outcome, the shooter rolls a total of 4, 5, 6, 8, 9, or 10. The shooter has done what's called establishing a point, and the game continues. Now we can subdivide this partition more finely. We subdivide the establishes a point according to what happens on the second die roll, and there are three different things that can happen. The shooter could roll a total of 7, in which case the shooter loses and the game's over, or the shooter could roll again the same point. If the shooter rolls a 4 on the first roll and a 4 on the second roll, the shooter wins, or something else can happen, in which case the game continues. And if the game continues, we can subdivide an event based on the first two rolls to make a still finer partition, and so on forever, because in principle a game of craps never has to end. You can do the same thing with coin tosses. This is nicely explained on pages 51 and 52 of the textbook. If you have 3 successive coin tosses, the courses partition is a sigma field that answers the question, what did you get on the first roll, a head or a tail? So an event will include 3 heads, 2 heads by a tail, head, tail, head, and head, tail, tail. A finer partition continues to pay attention to the first coin toss and the second coin toss, but ignores the third. So events like head, 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 and head, head, tail will be lumped together, and the finest partition of all pays attention to all three coin tosses. A representative event in this third sigma field includes events like you roll head, 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 or head, tail, tail. In the financial world, your sample space might be the collection of all the ways that the price of a stock can evolve on a day-to-day basis. The courses partition would pay attention to just what happens after the first day. The second will pay attention to what happens after day 1 and day 2, and so on and so on. This last topic is sort of optional, but I just want to try to convince you that it is reasonably straightforward to invent an event that you don't want in your sigma field. Here's how I'm going to do this. The real numbers in the interval 0 to 1 are an uncountable set, but the rational numbers in 0 to 1 are a countable subset of this uncountably infinite set. So we've got one countable subset of the real numbers in 0 to 1. Let's make another. Let's pick some irrational number. How about the square root of 0.2? And then add on to that all possible rational numbers and keep only the sums that lie in between 0 and 1. Since the rational numbers we added on are countable, this is going to be another countable subset of 0 through 1, and it doesn't include any rational numbers. It is disjoint from the subset of rational numbers. Clearly, if I pick any other real number in 0 through 1, for example, pi minus 3, this is going to belong to another such subset. Just add on all possible rational numbers and keep only the sums that lie in between 0 and 1. Of course, if I happened to pick a number that differed from my original x by a rational number, then x and y would lie in the same subset. So let's think about these subsets that are each generated by some number in the interval from 0 to 1. They meet the requirements for a partition. They're pairwise disjoint. That is, no two of them can possibly have any real number in common. And their union is the set of real numbers in 0 to 1 because every real number in 0 to 1 belongs to one of them. How many of these are there? Well, there must be uncountably many because, like the rational numbers, each of these is countable. If there were only countably many, a countable union of countable sets is countable, and therefore it cannot be the full uncountable set of real numbers in 0 through 1. Now, using these partitions, I'm going to create a so-called Vitali set. How am I going to do this? Well, I'll make the Vitali set V0. I have to make a choice of a rational number, and I'm going to choose 0. And then I choose one member from each other set in the partition. This is an application of the so-called axiom of choice, which says I'm allowed to invoke the concept of making a choice of element from each set in a possibly rather large collection. So I now have a set that includes 0, and it also includes a whole lot of irrational numbers, one from each set in the partition. And since I've chosen elements from an uncountable partition, and none of these can be duplicates, this set V0 has to be uncountable. Okay. Now I can choose some other rational number, something different from 0 in 0 through 1, and play exactly the same game. What I do is I add this to every element in V0, and if the result is larger than 1, I subtract 1 so that I always end up with a number between 0 and 1. Any number in 0 to 1 is going to belong to one of these sets, and therefore these disjoint Vitali sets are another way to partition the real numbers from 0 to 1. But now we've done something truly sinister. Each of these Vitali sets is an uncountable set. There's one of them for each possible rational number, but there are only countably many rational numbers, and so we have partitioned the real numbers in 0 to 1 as a countable union of disjoint uncountable sets. If we try to assign probabilities, we get into trouble. If we say the probability that a randomly chosen real number lies in a specific one of these sets is 0, then the probability that a real number lies in some one of them also has to be 0, but that probability also has to be equal to 1. We've got a contradiction. If, on the other hand, we say, oh, no, there's some very small probability that a randomly chosen number will be in a Vitali set, because there are infinitely many of them, the total probability in being in one or another of them ends up being infinite. The only way out of this problem is to say, we're not going to allow Vitali sets in our sigma field. And that ultimately is why we have to consider this concept of sigma field fairly carefully, because there are sets that just plain don't belong in any sigma field. So with that rather complex topic, I end this introductory video.